Great, thank you for having me here and for being interested about some of the research we're doing at Ancestry. So those of you who aren't familiar with AncestryDNA, we're a direct-to-consumer genomics company, and so if people are interested to learn more about their family history, they can order a kit online. It comes to their house, looks something like this, and then there's a little saliva collection tube in there, and they can spit half a teaspoon of saliva and send that back to our labs, which we then analyze to give them more information about their family history. So for this project, what we're interested in is this recent ancestry. So what happened in to the individual's ancestors in the last few hundred years. And I'm going to start just with the overview on what this project ended up as, to kind of give a vision of where this talk is going to go. So the first thing that we did was we discovered populations of people. For the example here, as you can see all these little white dots in Scotland. So this is a group of people who lived in Scotland and now have descendants who have taken the AncestryDNA test. So first thing we need to do is be able to find these people. And then we need to be able to associate customers with these groups so that we can mine our own data at Ancestry and then tell stories about how these groups moved around the world. So here you can see all these migrations coming out of Scotland going to places like Nova Scotia. And then the consumer can then connect with these stories and find out more about their ancestors through their genetics. Now, the reason why we can do this, and let's start with the motivation on how this is all going to work, is because we inherit DNA from our ancestors. So let's start with the little toy example here. I'm here at the bottom, and these two lines next to me represent my genome that I've inherited from my ancestors. So we all get our DNA from our ancestors, half from mom, half from dad. So let me introduce you first to just two of my ancestors, my second great-grandparents, Amandus and Bertha. So Bertha was born in the Sudetenland, which is present-day Czech Republic, and she has her two pieces of DNA that she inherited from her ancestors in the Sudetenland for generations, and they're the dark green and the light green here. So her sweetheart and her plan to move to the United States, he came first and she followed, and then he died of tuberculosis either before or after they were married. And so she moved to California, where she met Amandus, who was from northern Prussia, which is present-day Poland, and his DNA was from those German ancestors in the northern part of Prussia, the dark blue and light blue. Well, they got married and had 3 children before Amandus died in the Spanish flu epidemic in 1918. And one of those children was Fred Gleichner, who then, you can see his DNA is a mix of his 4 grandparents' DNA. And then that DNA was then passed down to me. So I have this little part of my genome, this DNA that I have, that I've inherited from people who lived at a specific time and in a specific place. And that isn't the end of the story, because like I mentioned, my great-grandfather had 2 other siblings, and some of those siblings got married and had kids, and then DNA from Bertha and Amandus were passed down to my cousins. Okay, so even if we didn't know about this whole tree, we can find these pieces of DNA in the genome where at the exact same part of the genome, there's the exact same piece of DNA, which implies that there were some common ancestors at some time in some place. Okay, so we find this piece of matching DNA that's been inherited, and we don't need to know anything about the family tree to know that me and my cousin share a recent ancestor in a recent time and place. Okay, so this is kind of the foundation that we're going to build on to be able to get to the product that I mentioned earlier. So now this talk is going to go in 2 different parts. So first I want to talk about some research that we published recently where we're discovering these ancestral populations using these matching DNA segments. And then move on to the second part of the talk, which is what we published here, is to be able to take those discovered populations and then build a scalable system that assigns consumers to these populations just using their DNA so that we can tell the stories about how the ancestors moved. Okay, so earlier this year we published this paper in Nature Communications, and this is going to be the first part of the talk because it's the foundation on which we're going to build out the rest of the talk. Okay, so our steps here is we're going to construct a network, we're going to find structure in that network with communities, and then we're going to annotate that structure with pedigrees. Okay, so The data that we're using for both of these projects is a set of about 700,000 anonymized individuals who've consented to research to AncestryDNA. The samples have been collected in 5 different countries. So our first step is to construct a network. So we have all of these pieces of matching DNA that we've discovered, implying recent common ancestry between individuals. So we can take some focal point individual and then look at their DNA matches in our data set and then build out a network. Once we have a network, then it becomes a community detection problem where we're looking for topology in the graph. So we use the Louvain method for community detection implemented in the iGraph package for this, and sure enough, we find community structure in this genetic network. So once we found the structure, we've only found it using the DNA relationships between individuals. So we actually don't know at first what this means. What are the forces that are keeping these groups of people together genetically over time? And so we need to look at some kind of annotating data to understand these different patterns. So at Ancestry, when a user submits their genetic sample to the company, they also have the chance to go online and build out their family tree. And so we have a lot of users who have spent years building out these detailed family trees going back 5 to 10 generations, and they can associate and say, this is the person in my tree who took this DNA test. And so they'll have information about their ancestors, including surnames, birth dates, birth locations, death dates, a lot of this information. And so we look at this information in aggregate in order to interpret what these different community structures that we've discovered mean. Specifically, we're looking at enriched birth locations or surnames. So we might look at a particular group and see that they have a lot of enriched birth locations, for example, in the southern part of Ireland. In Munster, Ireland, here you can see the dark red, highly enriched circles, and then the lighter yellow, less enriched throughout the rest of Ireland. Surnames also help tell that story as well. As my colleague in Dublin says, these are Munster Irish surnames that you would typically see in the southern part of Ireland. And so these enrichments that we're seeing in these different community structures give us a pretty good clue of why these people are connected genetically and what their common history is. So here's just kind of a big overview of some of the patterns that we've been able to find in our network as we found these structures genetically and then looked at the annotating birth location data. One comment that we get a lot is this east to west pattern across the United States. On the far right, you can see that kind of a rainbow shape. And we've worked with historians and found out that this actually is the way that the United States was settled. As people would start on the eastern coast, and then they'd follow friends and family across these migration routes across out west. Over time, and so that we see these patterns is not surprising. And just a bit of local information, you can see in Nova Scotia that you have both the blue dots from French Canada coming into Nova Scotia, as well as the green dots from Scotland showing up there. So we are seeing very consistent historical patterns reflecting the history coming out in the genetics. So that's the research that we're going to build on, is we're able to build out this network and discover these patterns. And now, how can we build a scalable system that's this blue arrow here that's going to take thousands of new customers coming in every day and look at their DNA to decide which groups they have ancestry from? So the requirements of our system are first, scalability is huge. So we're growing very rapidly. We have 5 million customers now, AncestryDNA, and it's getting bigger all the time. So how can we have a system that we can just plug these people into the system as fast as we can? And also we want to be able to continue to mine this network and find new structures and be able to replace old ones with newer structures as we learn more about this network. We need to have a consistent experience for the consumer so that every day when they log in to see their results, sans an update, that they are seeing the same thing. And on that same note, we spend a lot of our resources to work with historians to understand these different groups, their story over time, and we want that story to be consistent across the group. And we also want to be able, finally, to assign a customer to as many relevant communities as we can. So we're going to take our framework that we constructed earlier with the network annotated communities, and we add a classification step at the end here where we're going to assign customers to relevant genetic communities through classification. So I'm going to walk you through the 4 steps that we use in this process. I have a little progress bar here, which might help you keep track of where we are. But the goal here is to use the community detection results to create reference panels, use the relationships to calculate features, build classifiers, and then estimate the accuracy of the system. So first, let's use our community detection results to create reference panels. So at this point, here's another little toy example. So we have our original run of community detection. So we have these 63 different communities. I'm showing 3 here in these 3 different colors. And what we want to do is we want to find members of these communities who are good representatives of this population, the people who are most strongly connected genetically together. And so to find these groups of people, we use a bootstrapping approach. So we subset to 80% of the data, and then we rerun the community detection. And so we're going to find a bunch of new communities in this subset, and then we compare them back to the originals to see which communities they're most like. And then we can have, for that bootstrapping run, a set of communities that map back to the originals. So we do this 20 different times. And the result then is 20 sets of these subsetted community structures and how they map back to the originals. So individuals are then included in these different bootstrapping runs, and we can look at how the individual falls into these different communities to get an idea of how stable they are to any particular population. Okay, so another example, so this is our individual N here who was included in 16 of the 20 bootstrapping runs. 5 times this individual mapped to community 1, 11 times they mapped to community 2, and 0 times they mapped to community 3. So we created a set of rules here to label our members. So somebody who maps to a community 0 times is labeled as not a member of that community. Somebody who maps to community more than half of the time is labeled a member of that community. And then somebody who's between that 0 and 50, then we call them unknown, and we don't use them as a true example or a false example for that community. So based on these scores, then we have a label for each individual on which communities they belong to, and then for each community we have a set of true samples and null samples. So that's our reference panel data. So the next thing we need to do to be able to build this classifier is to have features that describe an individual's relationship to a particular reference panel. So let's talk about that next. So again, we have some individual here, and they have DNA matches to these different community structures. For example, this individual might map 3 people that are a part of community 1 in the community 1 reference panel. Now, when we find this DNA match, the length of that DNA match tells us about the relationship. So closer relationships are going to be longer pieces of DNA that are shared, and more distant relationships are shorter pieces of DNA that are shared. And each of those are reflective of different points in history. So we can label these matches. Then here I've labeled them as third cousins, distant cousins, fourth cousins, the relationships to these 3 people. So we can then count these relationships as our features. So we have our 3 communities for this individual, and then they match some number of individuals in each of these different relationship buckets. So this is information that our classifiers can use to find out what the structure of that community is in the network. So now we've built out our feature set, so we're ready to build classifiers. So we use a one versus rest strategy to train a random forest classifier for each community using cross-validation. And so we do this each community one at a time, and so that they are then one unit that can then be added to the production system or taken out. So once we've then built our classifiers, of course, the question is how well are they doing? One way that we can look at how well our classifiers are doing is by precision and recall on our testing set through the cross-validation. And what we're really asking here is, given the community detection structure and our reference panels, how well are we able to recover the network topology? And so we can calculate our precision and recall based on the labels in the testing set. Here I'm showing a few precision recall curves. I've taken the 63 communities for this study and ranked them by F1 score, and then plotted the min, the percentiles, and the max. So really what I'm showing here is that even in our worst case scenarios, we're doing very well. And in our best case scenarios, we're almost able to perfectly recover the network. But another thing that we wanted to do was do a completely independent validation of this approach that was independent of the community detection and the network and the genetics altogether. And so in order to do that, we looked at the family tree data that we had for these communities. And so you remember that people have built out their family trees, so we can look at people who have sufficiently large trees and try and get an idea of if they have ancestors born in the location of the community that we put them in. So for each of our classifiers, we ran the classifier and then took the people that were classified positive to the community and created a training and testing split. So 60% of the individuals were then our training set, and we used them to look at their birth locations in their family tree and find those locations that were enriched for this community. So in this example here, these are these orange diamonds on the map. These are locations that are specific to this community that we would expect people who are genetically associated with the community to have ancestors born in those locations. Then we take our test set, these 40 individuals, and we look at the percent of the assignees who have more than one ancestor born in one of these locations. So you can see the birth locations of the test set are all over the map a little bit, but they are kind of clustered around these orange diamonds. And when we look at specifically how many of these people have at least one ancestor born in this location, the concordance is actually really high, 95% for this particular community in Western Virginia. So this is just a distribution of those scores across the 63 communities. And records differ, and the user-generated content is different quality in different communities, but still we're seeing consistently that most of the communities have over 90% of the people with ancestors that they've discovered that are born in those locations, which is a nice independent validation of the whole approach. So today, we've now expanded on the system, and over 330 community classifiers are live online. So this work shows that by leveraging these communities discovered in this unsupervised way, we're able to build the supervised system that will take individuals and accurately assign them to these relevant communities, and that we then can build the scalable product that can rapidly add or take out these communities and customers as they come in. This course is a joint work with the whole AncestryDNA science team. Thanks to all of them, and we are hiring. If you are interested in the work we're doing, we'd love to talk to you. So thank you for your attention, and maybe we have time for questions.